Good evening. Welcome to lecture 13 of the tutorial session of Thermodynamics course by NPTEL Mechanical Engineering. So today we will be discussing week 1 assignment questions and week 2 assignment questions. First, we will start with week 1 assignment question. So this is as follows. So there is um, so this is a picture that shows cooking of rice in an open vessel on an LPG stove. They are saying LPG, but the picture is something of using wood and everything for cooking. Uh, okay, so the question is as follows. So make a neat sketch showing the vessel and the content inside it. So you can draw a vessel with some thickness, and then it is to this is just a schematic of what is there inside. So then water will be there, and then rice is inside, something of that sort you can draw. Then clearly show the system boundary. So system boundary, if we have to consider the thickness, I would suggest that we consider the inner boundary of the vessel, and then water and rice and everything will be the system, because that is what is getting cooked over here, and we are more interested in observing the cooking of the rice and water. That is what is of our interest, so that is our system. So if that is a system, then what is bounding around that system is surrounding. So the inner boundary of that vessel is the system boundary. Okay. And so what is included and what is not included? So what is included is the inner part of the vessel. That means the water, rice, and the inner boundary of the vessel. And what is not included is the heat source and stove, and the rest of the things in the surrounding. So that is the surrounding. Now, identify mass inflows and mass outflows. So mass inflow will be like, if you are considering rice and water is already present inside the vessel, then you are not adding anything. That means mass inflow is nil or zero. Mass outflow, if you think of it, uh, so um, they are mentioning it is an open vessel. That means mass outflow will be steam. Steam will be coming out of the vessel when while the food is getting cooked. So that steam will be mass outflow. Now, the next question is heat and work transfer. So heat transfer is occurring, obviously that is how it is getting cooked. So heat transfer, so heat inflow is there uh, from flame to the vessel. So heat inflow, yes, that is there. And work done by the system. So we know that, okay, when a vessel is closed and water is boiling inside, then the lid will be moving because of the steam pushing it outwards. But that work is very negligible, because the ds distance that the steam is moving that lid is very negligible. So you can consider that the work um, done is negligible or not there, not present. Now, uh, is this an open, closed, or isolated system? It is an open system. There is, because there is a mass outflow and energy transfer, also heat inflow. Then, um, so this is open system. Then which approach will you use to write the governing equations, the control volume or control mass? So for open system, it's always control volume approach. Okay, so control volume, because volume will be constant, not the mass, because if there's a mass outflow, that means water is evaporating and escaping the system. So the mass will not be constant always, so you cannot use the control mass approach. Now, next question, is this system in equilibrium? If not, then can it be approximated as being in quasi-equilibrium? So system is not in equilibrium, because continuous heat transfer and boiling and everything is happening. So not equilibrium. If temperature and pressure changes are like very slow, then we can approximate it as quasi equilibrium for sure. Then if the system is in steady state, if not, again, can you approximate it as quasi steady state? So steady state analysis, it is not, because again, not steady state because of the heat and mass transfer that is happening, that is changing with time. So if you measure the amount of water inside the vessel at t equal to t1, and then if you measure it after some time, like maybe say 5 minutes, and that is like t equal to t2 at a different time point, you can see that the amount of water or the mass of water inside the vessel is different. So it is changing with time, like uh, the properties are changing with time, so it is not steady state. Okay, not steady state. Now again, if the mass transfer is very slow, then obviously you can approximate it as a quasi steady state, so that approximation will hold, or it will be valid. Now next question, write one question whose answer you would like to have from a complete analysis. So as we have defined the system as water and rice mix, that means we are observing the change happening in that food mixture which is kept for cooking. So we can say something like how much time will it take for cooking if the heat input is so and so, or if you want to cook this within 20 minutes, then how much of heat input should be given. um, then like uh, the study will be like heat input rate versus time. Those studies can be conducted for the system. Now, uh, next question is JK. Thermal efficiency of this process can be defined as fraction of energy released by combustion of wood that is taken by water in the vessel. Do you think this is the value of thermal efficiency? Okay, thermal efficiency. Okay, before okay, it was supposed to be I. Then there is J question is also there. Okay, what fraction of households in India use wood as fuel for cooking? It will be very less because of the new uh, I mean, plans and programs that government has started, like Ujjal Yojana and all, which is creating the subsidized LPG gas connections to people who are underprivileged. So most of the people have shifted to something we call it as LPG gas, like the without relying on wood or subsequent materials for cooking. Uh, LPG, why we are preferring is because it is less polluting, like it is more of a cleaner fuel compared to wood. So that is a good shift of uh, in the direction of reducing carbon footprint. So yeah, so the fraction will be very less, maybe like 10 to 20% will be what will is a fraction of households in India that are relying on wood as fuel for cooking. Then yeah, K question is thermal efficiency of this process. Okay, so they are saying efficiency is equal to, or efficiency we will say it as eta is equal to useful energy to water or the cooking material um, divided by energy from fuel. That is the definition given in the question. Okay. So they are saying thermal efficiency of this process can be defined. Eta thermal can be defined as fraction of energy released by the combustion of wood that is taken by water in the vessel. So what do you think is the thermal efficiency? So we can say that energy of fuel. energy from fuel, when it is getting combusted, it dissipates into the surrounding. So if you're seeing it, the stone will be getting heated, the surrounding air will be getting heated. So this heat is getting dissipated everywhere, and only a part of heat will be going to the vessel. Again, the thermal conductivity of the material uh, under consideration will also affect the heat transfer that is happening. So most of the heat will be absorbed by the vessel itself, and only a part of that will be going to uh, the cooking material, the food that is inside the vessel. Also, the chemical energy of fuel, like the complete chemical energy, it won't be getting transferred into heat energy form only, because first thing is incomplete combustion that is happening, because you can see there is a lot of soot and everything. So soot means the carbon deposition that is happening, because the whole of the carbon is not getting combusted. So that means there will be carbon deposition, so that so incomplete combustion is there, so the entirety of chemical energy is not being converted into heat energy. Then second thing is, this incomplete combustion is like it is being shown out in the form of other oxides like carbon dioxide and carbon monoxide. So carbon monoxide is also a um, partial combustion. Carbon dioxide is the complete combustion material. So in different pathways, this chemical energy is getting transferred. There will be sound energy also. When you are burning something, it will be like cracking in between. So sound is also there. Then as light also, it is getting emitted. So different radiations and convection and conduction, through different modes heat is getting transferred. So only a very small part, maybe like 1/3 of the energy is getting transferred to the cooking material. So I would say that it will be around 30 percentage. Okay, around 30 percentage. Okay, now next question. Okay. Okay, so second question is as follows. One second, let me paste the question over here. Okay, okay, it's taking some time. Yeah. Mm. So picture of a cooling tower is shown below. Consider the entire inside space as a system with hypothetical surfaces across the air and water. Uh, and okay, surfaces across the air and water flows across the system boundary. Now make a cross-sectional view of cooling tower. So I'm assuming it's something like this. So there will be this is a cross section of the cooling tower. And they are saying there are surfaces, uh, okay, inside, which is like okay. So water flows across the system boundary. So this is the system boundary. Okay, and water is flowing across that. Okay, and air is flowing across the hypothetical surfaces. So air is flowing across them. Okay. Now, clearly show the system boundary. Uh, Clearly show the system boundary and explain what is included and what is not. Clearly identify the hypothetical surfaces. So, the external environment outside the cooling tower, that is not included in the system. So, whatever is The system boundary is near the water flow. So from there onwards, and the hypothetical surface and the airflow, everything is inside the system. Okay. Then mass flow across the boundary. So if we are considering there is this water flowing, so we can think of it as this way also. If you're taking a side view, it will be like this. Okay. And water is flowing. Okay, water is flowing inside this frame. This is a cross section view. Okay, water is flowing inside the this frame. So inlet will be somewhere around here and outlet will be around here. It will be like circulating, and air will be like passing through some tubular structure over here. Okay, likewise there will be, and this is what is going to cool the water in the frame. Okay, so this hot water that is coming inside, water in and water out. So there is sort of a mass flow that is happening, and incoming air. So air is also getting in and it is also going out. So that is also sort of mass flow. Then heat transfer is happening from air to water or water to air. So if water is treated as the hot thing over here, and water is getting cooled by convection of air, then we can say that water heat transfer is happening from water to air. Then work input is negligible if you are not thinking about pump and everything inside the system. Or outside the system. So if there is a pump or something, then there is some electrical work done. Otherwise, there is no work done. Then system classification. So there is heat transfer and mass transfer. So it is an open system. So this is open system. Heat transfer is there. Uh, then mass transfer is also there. Heat and mass transfer is there. It is an open system. Would you select control volume or control mass approach? We will select control volume approach. Then identify application of cooling towers and purpose they serve. So we use this cooling towers in mostly power plants. Then this HVAC systems like ventilation air condition system, and then industrial cooling for some purposes. There and all we will be using cooling tower. And then the same thing, where and all cooling towers are used, thermal power plants, chemical factories. So those are the places where we use cooling towers. Next question. So this is about diesel generator set. So there is a one second. So there is a DG set shown below. An engine jacket, water is cooled in a radiator. Engine is coupled to the generator, and entire arrangement is enclosed in a chamber that reduces noise pollution. So that is an acoustic enclosure. Diesel tank is below engine. It is regularly filled. Make a neat sketch of the system boundary that includes the entire acoustic enclosure as a system. Briefly describe the system surface. Okay. So diesel engine will be having a fuel input. I'll just draw. Okay. So fuel will be given as an input. So there will be fuel tank from where this fuel is supplied. Then there will be an engine. Uh, so fuel is going to an engine. Engine. Then from that engine, this engine will have this piston cylinder arrangement, which is connected to a shaft. That shaft will go to a generator, mostly like as we have learned in school and all. There will be a rotor stator kind of setup which will generate electricity. So this thing will be rotating in a magnetic field, and then electricity is being produced. So this is the generator setup, and then this heat from engine will be going to something we'll be calling as radiator. Okay, so heat will be going here from engine to radiator. So the entire setup will be inside a acoustic enclosure. Okay, so this is the enclosure. So this will be the system. So for the above system, show all mass transfer, work and heat transfer. So mass in will be diesel. So we will be opening, there will be a lid over here. We will open it and we will pour the diesel into the diesel tank or the fuel tank. Okay, so mass in is there. So mass flow, mass in is fuel. Then mass out will be there from radiator. There will be exhaust will be there. So mass out is exhaust. Then energy. Energy in is here it is chemical energy. And energy out is mechanical. Sorry, electrical energy. From the generator, what is happening? Current collectors are there. So electricity will be produced. Is this an open or closed system? It is definitely an open system because mass flow is there, energy flow is there. So open system. Then use of okay, identify uses of the set. So this is for emergency, electrical backup, especially in places of very importance like hospitals, construction sites, or industries. There and all we will be using diesel generators. Now, next up is okay, this question number 4. Question number 4. Some processes are described below. Classify these are reversible or irreversible. If the process is irreversible, then under what condition, if any, can the process be approximated as a quasi-reversible process? Which of these processes can be considered to be internally reversible? Make sketches showing the system boundary and show the different states. So say, first one is cooling of freshly cooked idli on a plate in a room. So that is sort of irreversible, because if you consider, you can heat up the idli again, so it will come back to the temperature, the previous temperature, but then heat that was dissipated to the surrounding, if you think of it, that heat cannot be recovered. So in that manner you can say that this is irreversible, because reversible system means you can um, take the system back into the same state from where it began without causing any changes to the system or to the surrounding. So that is why you cannot say that this is a reversible process. It is irreversible. It can be quasi-reversible if the cooling rate of cooling is very low, which is always the case. So so that is why even though most of the um, real life scenarios are uh, irreversible, for the sake of our analysis we can approximate most of the problems as quasi reversible. Okay, Now, LED bulb process, again, it is irreversible because whatever electrical energy we are providing to LED bulb, it is getting dissipated in the form of heat and light energy. So that cannot be recovered back. So that is irreversible. Water flow in pipe, you can say that it is irreversible because of frictional losses. So first one is irreversible, second is also irreversible, third is also irreversible, but this can be quasi reversible. This also can be quasi reversible. This LED bulb is not that quasi reversible because heat and uh, light, I mean, energy which is getting dissipated is happening at a faster rate. So we cannot say it like that. Maybe heat transfer, it is, we have to check according to what sort of a condition that we are thinking. For example, in a in a power plant, okay, this LED bulbs are used as an indicator. So compared to the kilowatts and megawatts of power that we are considering over there, the power output or the power that is consumed by LED bulb is something which is like very low, that we take it as like, okay, it is not rapidly heating or rapidly cooling system, that whatever is happening over there, we will be taking it as a reversible process which is not contributing to something called as chaos or disorder, or that term I don't want to speak now because that's not discussed earlier. Okay, now water flowing in a pipe, it is irreversible because there are a lot of friction losses in pipe wall. So that is why we are taking it as irreversible. Then it can be quasi reversible if the flow is like very smooth laminar flow. uh, Next is inflation of tire, again irreversible. Inflation or deflation, if you see, if you are using a electric pump or something to pump the air inside, that is a very fast process. So you will be seeing that a lot of heat dissipation is happening when you touch the tire or that area. You can see a bit of heating up is happening, and also the flow of air will be turbulent. So again there will be frictional losses. So that is irreversible. Again, if it is like slowly pumped inside using a hand pump, and there is a sort of a, it will never be smooth flow, it will always be turbulent flow because it it is expanding using a nozzle inside. So I think it is always irreversible. Now, next is solidification of molten metal. So cooling is a very rapid process. It any So there are different cooling methods, right? Um, Oil cooling, water cooling. Depending on that, the rate of cooling is somewhat different. Even then, um, we as we know, when uh, the salt molten metal, if you are seeing, the temperatures are really high, and we know by radiation laws and all, it is like T to the power 4 is the uh, rate, it is at the fourth power of temperature, the rate of cooling is happening. So T will be like really high for molten metal, around 800 to 1000 Kelvin. It will be 800 K to 1000 K, or even more than that. So if that sort of a temperature that we are dealing, then rate of and steel and all, I think it is about 1000 degrees centigrade. So T to the power 4 rate will be really really high. So that is an irreversible process. Okay, now fifth question, make a sketch of the devices or equipment described below. Draw a system boundary and identify if the system is in equilibrium or in steady state. Give brief justification for each case. Comment whether the quasi equilibrium or quasi steady state assumptions are justifiable. The matter of interest is listed in brackets. Okay. So first is air compression, in air being compressed in a bicycle pump. So bicycle pump is okay, space occupied by the compressed air inside the pump. So it is not in equilibrium because pressure changes are there, pressure changing, so not equilibrium. And is it steady state? No, because there will be variable rate of compression. So that is not steady state. Then can assume quasi-equilibrium if that is a slower rate of compression is there. A closed room in which indoor unit of split AC is operating. So split AC, if you like if you switch it on within initial few minutes, the temperature of the room will be constant. Whichever temperature we are setting the air conditioner to, that temperature will be maintained. So the temperature of the room will be steady after uh, initial few minutes or seconds. So that is steady state, but not in thermodynamic equilibrium because there's mass inflow, mass outflows, and all those things. So there is a mechanical equilibrium is not there. Even though thermal equilibrium is there, mechanical equilibrium may not be there. Uh, and coolants and everything is working, so there won't be chemical equilibrium also. So there won't be thermodynamic equilibrium. So it is not in equilibrium. Next is a cup of hot tea placed on a table under a ceiling fan. So hot tea under fan, it is not in equilibrium because cooling process is happening. So thermal equilibrium is not there, so it is not in equilibrium. And steady state, it is again, it is not steady state because temperature is varying with time. So again, not equilibrium and not steady state. This one is equilibrium. Okay. Steady state is there, but not equilibrium. Steady state, but not equilibrium. Uh, Next up is a spoon dipped in a bowl containing hot soap. So spoon will be getting heated up, but you can see that if you dip a spoon in a bowl of hot soap, the temperature after some time it will be uh, not changing with respect to time for the entire spoon. So that is steady. So it is steady state, but not in equilibrium because heat transfer is happening between the hot soap and bowl. Not in equilibrium. Your cell phone when in use. Okay, my cell phone when in use, it is steady state if I'm continuously using. If I'm switching it on and off within a small amount of time, then that is not steady state. But steady state if continuous usage is there or continuously it is switched off, it is steady state. And equilibrium when we are using the chemical energy of the battery is converted to electrical energy, so chemical equilibrium is not there, then slightly it will be heating up, so thermal equilibrium is not there. Mechanical, if you are moving it around or those things are there, then mechanical is also not there, so this thermodynamic equilibrium is not there, so not in equilibrium. Now sixth question, the gauge marked in kilogram per centimeter square is connected to a tank. An operator records it as 2.1. Ambient pressure is 751 mm of Hg. What is the absolute pressure in the tank? What is the why is the wall provided? Okay. So this we have to refer to our previous lecture on different types of pressure measurements. atmospheric pressure. Yeah. So we know there is something called vacuum pressure, which is absolute zero. So vacuum. Then there is atmospheric pressure somewhere over here. Okay, this is atmospheric pressure. Uh, I'll draw it somewhere in another manner. So this is atmospheric pressure if we see. Okay. Now I'm taking 2 points over here and over here. Okay. So this measurement with respect to atmospheric pressure. So this is atmospheric pressure. Okay. And this is gauge. This is also gauge pressure. So whatever pressure we are measuring with respect to atmospheric pressure is called gauge pressure, and whatever pressure we are measuring with respect to vacuum is called absolute pressure. Absolute. So this is absolute. This is absolute. Absolute pressure. So here the absolute pressure of this atmospheric pressure is equal to atmospheric pressure. Here the absolute pressure is something else for this gauge pressure, for this point. And if you are measuring from the atmospheric pressure with respect to atmospheric pressure, that is called gauge pressure. Here the gauge pressure will be negative, here the gauge pressure will be positive because it is above atmospheric pressure or more than atmospheric pressure, that will be positive gauge pressure. Whatever is like lesser than atmospheric pressure will be negative gauge pressure. So question here is gauge, the gauge is marked in kilogram per centimeter square, and it is connected to a tank, and operator records it as 2.1 kilogram per centimeter square. Ambient pressure or the atmospheric pressure is 751 mm of Hg. What is the absolute pressure? So absolute pressure is what? Absolute pressure. Okay, we'll first convert everything. So here gauge pressure is given in kilogram per centimeter square. Gauge pressure equal to 2.1 kilogram per centimeter square. Now SI unit, if you want to convert, 2.1 times 98.0665, which is equal to 205.94 kilopascal. Okay. Now atmospheric pressure, it is given in mm of Hg unit. So that also we have to convert to kilopascals. So PATM, we will take this as P gauge. PATM is 751 by 760. 760 mm of Hg is 1 atmosphere times 101.325 we will be taking. So that is around 100 kilopascal. So absolute pressure is equal to Pg plus PATM. So you can see here, this is like absolute pressure. If I'm taking this as gauge and this is atmospheric, so absolute pressure for this one is gauge plus, so this part will be Pg and this part will be PATM. Okay. So here that will be around 205.94 0.94 plus 100.09, which is equal to 306.03 kilopascal. That's the answer. Now, next question. A differential manometer is mounted in a vertical position and its appearance is shown below. On an attached meter scale, left leg reads 7.9 centimeter and the right leg reads 44.5 centimeter. 1 second, I'll take it to the next page. Okay, never mind. Calculate the pressure difference in kilopascal. Okay. So first question is what? So this right here reads 7.9 centimeter and this is 44.5 centimeter. So we know the hydrostatic pressure is rho GH, and here if you want to find the difference between P1 and minus P2, so P1 is, so I'll take this as H1, this is H2, so P1 is rho GH1 minus P2 is rho GH2. Both are having the same material, the water, okay, so this is having some liquid inside and both so both like are having the same liquid, so rho is constant, G is constant. We'll be taking it as H1. Okay, 1 second. Okay. So H1 minus H2, and here so we'll be getting negative, so we'll be taking P2 minus P1 equal to rho G H2 minus H1. Okay, so we just have to calculate H2 minus H1 and then multiply with density if it is given, density times G, that is 10 or 9.81 times delta H we have to do. Okay. So if you are taking the liquid to be mercury, it will be around, mercury rho is, okay, then G is 9.81 and H2 minus H1 here is 44.5 minus 7.9, which is equal to 36.6 centimeter. Okay, so if we calculate, that will be altogether 48.79 kilopascal. Okay. Now, is this gauge pressure or absolute pressure or neither? So you can see this legs of this manometer is open, so that is exposed to atmosphere. That means it is with respect to atmospheric pressure, so it is gauge pressure. Now, next up is pressure. Okay. One second. Pressure cooker blows its whistle at 1.5 bar. At what pressure is the food getting cooked inside? The pressure cooker is being used at an altitude of 5000 meter where ambient pressure is 54 kilopascal. When the whistle blows, what will be the pressure inside the cooker? Okay, first up, so 1.5 bar is gauge pressure. Gauge pressure is 1.5 1.5 bar because it is measured like it is inside pressure of the cooker. So that is 1.5 bar or 150 kilopascal. Then absolute pressure at sea level, we have to take it as atmospheric pressure at sea level is around P-atm at sea level is equal to 101.325, that is a standard value, kilopascal. Now P absolute will be gauge plus P atmosphere, Pg plus P atm, which is equal to 150 plus 101. It's 251.325 kilopascal. Okay. Now at 5000 meter altitude, 5000 meter altitude, ambient pressure P atm, they are saying it is 54 kilopascal. So it has approximately half. So P absolute we have to calculate, that will be around the gauge pressure hasn't changed, so 150 plus 54 is equal to 204. So what happened is with altitude, the pressure with which the cooker cooks food has changed, like 50 kilopascal, approximately 50 kilopascal of pressure has reduced. So cooking time increases at high altitude because the pressure is less, so cooker cannot. So as we have seen in many devices like autoclave and all, what we are doing is we are trying to reduce the temperature that is required to boil using pressure. But with the pressure lowering, the temperature required to boil will be higher. So to reach that temperature, you have to give a heat input. So heat input is always constant. If it is at 5000 meter altitude also, if it is at sea level also, we are using almost similar stove and everything. So heat input will be like a constant value and pressure has varied. So temperature requirement is higher in high altitude. That means we have to prolong the process of giving heat so that the system reaches that temperature. So that means cooking time has increased. Okay, cooking time increases. Okay, now last question of week 1 assignment. Okay. Water flows through a set of tubes over which hot gases flow. The gas is cooled. Uh, the gases cool down by transferring energy to the tube, which in turn transfers the energy to the water flowing inside it. Okay. The arrangement for one tube is shown below. It is desired to study the water as it flows through the tube. Which of the following system boundaries is best suited for this purpose? Give supporting solution to supporting reason in each case. Okay. So best choice, we have to think about how to analyze the heat flow that is happening to the water or from water. Okay. Okay, to the water, because hot gases, so the question is hot gases are flowing over this tube which is containing water. Okay, so hot gases, it will cool down by transferring heat from gases to water. Okay, so we should select the system boundary such that we can see how much of the heat is being transferred into the water. So in case A, if you see the whole of the system, uh, if we are taking a system like this, system boundary like this, what is happening is gases are here also. Okay, so heat transfer from here to here may not be there, because this is also hot gas, this is also hot gas, so there won't be any heat transfer. Heat transfer happens only when temperature gradient is there. Heat transfer is actually happening at the tube boundary, and that phenomena cannot be studied, because if system boundary is here, we are always studying heat transfer etc as a boundary phenomena, and if we are not keeping boundary above this tube, you cannot see the heat transfer that is happening across that boundary. So you have to select the boundary such that the tube walls are on the boundary. Okay, so it is I don't understand the difference between B and D. Yeah, okay. Oh, okay. So if you want to, this is for a small element inside that water, but water heat transfer is happening across this much boundary. Okay, so you need to select B as your system boundary. Only then you will get the entire heat transfer that is happening across the boundary. Okay, so this whole influx vector we will be calculating. So that is the system boundary. So that is answer is B. Okay, so week 2 assignments. Okay, first up, okay. So week 2, first question is, a tank is being filled with oxygen with the rate of 0.07 kilogram per second, and at the same time oxygen is being drawn from the tank to fill 4, okay, 1 second. Fine. Okay, question is, tank is being filled with oxygen at the rate of 0.07 kilogram per second, and at the same time uh, oxygen is being drawn from the tank to fill 4 oxygen cylinders at the rate of 0.02 kilogram per second per cylinder. At some point in the filling process, the mass of oxygen in the tank is 10 kilogram. What is the rate of change of mass in the reservoir? What is the time required for the mass inside the tank to be 15 kilogram? Okay, so oxygen inflow rate, so this is the cylinder that we are talking about. So oxygen inflow rate is 0.07 kilogram per second. Okay, then this is being uh, given to 4 different cylinders from the cylinder at 0.02 kilogram per second per cylinder. Okay, okay. Uh, so mass in the tank at a certain instant is 10 kilogram. Now we need to find the rate of change of mass. Okay, so rate of change of mass is dm by dt. dm by dt is equal to mass in minus mass outflow. Okay, well known equation. So mass out, the rate of mass going out is 4 times 0.02, which is 0.08 kilogram per second, and mass in is 0.07 kilogram per second. So dm by dt is going to be negative. Okay, it is 0.07 minus 0.08, that is equal to negative 0.01 kilogram per second. So mass is going to deplete. So after every second, 0.01 kilogram of mass is going to be less in this main reservoir cylinder, which is having 10 kilogram at present. So if it is depleting, it is never going to increase to 15 kilogram. So the answer for the second question is never. So time required is not at all a question because it is depleting. The question should be like, when will the tank be getting empty? So rate of change of mass in the reservoir is 0.01 kilogram per second, negative. Okay. Next question is battery bank. Okay. So battery bank or power bank. 10,000 mAh battery bank is charging a cell phone at a rate of 15 watt with a voltage of 4 volt. What is the rate of change of internal energy of the battery? Express the capacity of battery bank in joules or kilojoules. After how many hours of continuous operation at the above rate will be the battery reach 10% of its capacity? Okay, it's a very good question. Okay, so battery capacity is given. Capacity is 10,000 mAh. Okay, so 10,000 mAh means milliampere hour. So milli means 10 to the power minus 3, that is 10 ampere hour. Okay, now voltage is 4 volt, charging power is 15 watt. So at the rate of 15 watt, the power is getting consumed. Now capacity to joules, how to convert? So energy equal to, one second, energy equal to charge times voltage, okay, which is equal to charges one second, yeah, 10. So it is given ampere hour. Ampere is, so 10 is the value of capacity. Ampere, so 10 ampere per hour. So hour to second we have to convert, that is 60 times 60, that is 3600, 600. Then okay, times voltage is 4. So this is the energy. Energy is 144 kilojoule. Okay, now rate of change of internal energy we have to calculate. So du by dt equal to 15 watt, that is the power at which it is charging. Power means energy by time, that is energy is internal energy is u. So change in internal energy by time taken is going to be the power with which it is charging. So that is 15 watt. 15 watt equal to 15 joule per second. Okay, now time for battery to reach 10% of its capacity. So battery bank will be t equal to 14400 divided by 15, which is equal to 960 seconds, because it's joules per second. So you will be getting 960 second divided by 60, you will be getting 16 minutes. Why we have taken, so this is 144 kilojoule equal to 144000. Okay, 10% of this is 14400. Okay, 110 is dropped, then divide by 15 is giving 960 seconds. that is equal to 16 minutes. So with, okay, so what we have done is energy capacity is given. Capacity is given in ampere hour. So energy we know is charge time voltage. So that is equal to this capacity times hour is going to give you current. So it is like, okay, 1 second, 10 ampere hour times, yeah, 10 ampere hour I have converted it to 10 ampere second, and then times volt will give you the charge, I mean energy in joules or kilojoules. Okay, then we are seeing how much, like uh, how much of the energy is being taken per second. So that is 15 joule per second. So you divide the entire amount with the amount at which it is getting subtracted. So that will give you the total time. Okay, now next question. A woman is kneading dough by pressing it with her hand. In one stroke, the pressure applied is 5 Newton and hands move 100 mm into the dough. This action is repeated many times. During the kneading process, the dough gains 10 joule from the warm air in the room and the woman's hand as heat. Calculate the work per stroke of kneading. Calculate the rate of change of internal energy of the dough. Okay. So what are the, okay. So the data given is force applied is 5 Newton. Then displacement or S is 100 mm. So work done we can easily calculate, which is force times displacement. Okay, displacement which is equal to 5 times 0.1, which is equal to 0.5 joule. 0.5 joule. Now internal change and internal energy change according to first law is delta equal to Q plus W. Q is from uh, heat transfer from the atmospheric air to the dough, that is 10 joule, it is given, and from hand also. So heat from her hand and heat from the ambient air is 10 joule plus work is 0.5 joule, so it is 10.5 joule. That was a very direct question. So there won't be any considerable energy change because of this kneading, but then yeah, 0.5 joule will be added. So A and B is done. Now fourth question. A rigid vessel has a electric heater inside it. Okay, a rigid vessel has an electric heater inside it. It contains a fluid whose internal energy is 2500 or 2500 kilojoule. The heater is operated at 800 watt power for 7 minutes. During this time, the vessel loses heat to the surrounding ambient air at the rate of 2 watt. Calculate the internal energy of the fluid after 7 minutes. So this is the fourth question. Okay, so the question is, there is this rigid vessel which is having an electric heater inside it. Okay, it contains a fluid whose internal energy is 2500 kilojoule. Heater is operated at 800 watt for 7 minutes. So this time the vessel loses heat to the surrounding ambient air at the rate of 2 watt. Okay. Okay. So we have to calculate the internal energy. Cool. Okay. So initial internal energy is, initial U is 2500 kilojoule. Then heater power equal to 800 watt, and time equal to 7 minutes equal to 7 times 60 is 420 seconds. Okay, 7 minutes. Okay, now heat loss is 2 watt. So heat provided to the water is 800 watt times 420 second is equal to okay, 800 times 420 is 33630. That is 336 kilojoule. Okay, this is in joules, this is in kilojoule. Now Q out or Q loss is at the same time we are calculating. So 420 second, that is equal to 840 joule. That is 0.84 kilojoule. Okay, so final internal energy is delta U equal to U initial plus Q in minus Q out, which is equal to 2500 plus 336 minus 0.84, which is equal to 2836 minus 0.84. So minus 0.84 will be 35.16. Okay, kilojoule. That will be the answer. Now, fifth question. The picture of a syringe during use for inoculation is shown below. The force applied by the nurse is 1.2 Newton, which is constant throughout the travel of the piston, which is 40 mm. So force is given, displacement is given. You can calculate work. Then considering the vaccine as a system, so inoculation is vaccination. Considering the vaccine as a system, make two sketches, one of the start of the injection process and another midway through the process, and show the system boundary. Calculate the work done by nurse. Okay, so piston cylinder arrangement, so this will be the system. Okay, so inner wall of the piston will be there. Sorry, I don't want to take this much. Okay, so this will be the system boundary. So vaccine is the system. So it will be enclosed by the cylinder walls, or yeah, the cylinder of the syringe. So that and the piston will be the upper boundary. Okay, so this is the system boundary, and if it is pressed some more inside, one second. Okay, if it is pressed some more inside and the piston reaches somewhere here, then that will be the newer boundary. That's it. That is the only difference. Work done will be what? 1.2 Newton times 40 mm. 40 mm you have to convert it to meter and then multiply. Okay, so that is 0.04. It will be around 0.048. So nurse is not doing much work. Just kidding. Yeah. So that is about the first 5 questions of week 2. Now the next set is the 6th question. So yeah, a balloon is inflated from an initial volume of 2 liter to a volume of 3 liters. The internal pressure was 50 millimeter And above, okay, this WC is water column above ambient pressure, just like with of Hg, this is of water column. Uh, During the inflation process, the ambient pressure remains constant at 750 of Hg. 1 second, I need to take a call. Mm, okay. Okay, so calculate the work done by inside air on the balloon, and calculate the work done by the balloon on the surrounding air. Okay, so the question is, there was a balloon which is getting inflated, so it is going here. Okay, so initially it is 2 liter, then it is 3 liter of volume. Okay, and so 2 liter we can convert it to meter cube, so 0.002 meter cube, and 3 liter is 0.003 meter cube. Internal pressure, so pressure inside the balloon initially was 50 mm of water column, that is 50 mm of water column, so you have to convert it into Pascal. So conversion is like, you will be multiplying it like rho g h, okay, to get it in Pascal. So the value is 490.5 kilopascal. Okay, so rho for water is around 1000, and G is 9.8 and H is 50 mm. So when you multiply it, you will be getting 490.5 kilopascal. Ambient pressure is 750 mm of Hg. Again, rho GH we will be using. So rho is 13.6 or 13,600 kilogram per meter cube. 13.6. Okay. Then G is 9.8 and H is 750 mm. So you'll be getting around, what will be the kilopascal? Around 100,000 Pascal. Okay. Now, work done by inside air on balloon will be W equal to, so we have to find force. Force is pressure times area. Area is, we are taking it as now change in volume. Okay, okay. No. Okay, instead of force times displacement, you can take it as PdV. Okay, so PdV is pressure, is internal pressure of balloon we have to take. That is this 50 mm of water column, that we will consider it at kilopascal, 10 to the power 3, times dV is 3 liter to 2 liter, 0.0032 to 0.002. Okay, that is equal to 0.49 joule. Now, work done by balloon on surrounding air. So what is happening? Balloon membrane is pushing the ambient pressure, that air around, and then it is expanding, right? So that expansion is happening against ambient pressure, ATM pressure. Okay, so ATM pressure is trying to compress it, but this is expanding. So here the W is going to be PATM. Okay, PATM times dV. So dV is same, PATM is this 1 lakh Pascal or 100 kilopascal. Okay, so 100 kilopascal times dV, which is equal to 100 joules. Okay, So that is the sixth question. Now, seventh one. A cylinder piston arrangement shown below encloses a fluid. The cylinder and piston have leak-proof mating and there is no friction between them. Surrounding air pressure is 50 kilopascal. The inside diameter of the cylinder is d mm and piston mass is m kilogram. In the initial state, state 1, the length L equal to L1 meter and substance is heated and the piston rises to just touch the stops. This is state 2 and the length L is L2. The substance is further heated such that it attains state 3 where the internal energy is doubled that of the internal energy at state 2. Write expression for heat and work for each of the process, like from state 1 to state 2 and state 2 to state 3. Okay, so what is happening is you have got some substance inside a cylinder piston arrangement and then you're heating it up so that with that heat the substance is expanding. So initially the piston was at L1 meter distance from the cylinder, like bottom of the cylinder. Then with this heat supplied, the substance expand and it pushes this piston upwards. So this heat is converted to work without any change in internal energy. Okay. So it is directly whatever heat is being supplied that is converted into work and it is directly pushing the piston upwards and finally it reaches here at L2 distance. Now what is happening? At L2 distance, uh, there is a stopper. So piston is not allowed to move further. That means without displacement there is no work done, or without volume change there is no work done. dV equal to 0, that means W equal to 0 because W is P dV, right? Now what is happening with this stopping of piston? The work done is 0, so whatever heat is coming inside, so according to first law it is a delta U equal to Q plus W. So Q was given and so initially from state 1 to state 2 what was happening is Q is applied which was uh, going to W, so Q equal to W and hence delta U equal to 0. Okay, but from 2 to 3 what was happening is 2 to 3 W is 0 because of stopper. So whatever Q is given that is going to delta U. Okay, so internal energy was changing and it became double of the initial one. Okay, now we have to find the equations and everything for this one. Okay, so process 1 to 2, what is happening? Work equal to force times displacement, which is equal to Q. Okay, and process 2 to 3, heat equal to change in internal energy. This is the concept. Okay, so those are the equations for question number 7. Okay, now if you want to quantify, the values are given, but yeah, expression with respect to expression only you can take it most of the time. This is a hint for question number 7. Now, question number 8. A plastic sachet contains m kilogram of a phase change material. Such sachets are used for medical purposes and for keeping chilled food items cool and during delivery. There was a picture of this plastic sachet. I haven't taken the picture. At some instant, the contents are in state 1 and in this state, the entire PCM is in liquid phase. So state 1 is liquid phase. Okay. Now, and in the state, the entire PCM is in liquid phase and its mass is M1L. The sachet is cooled in a freezer and it attains state 2 where some of the liquid is frozen and mass of the liquid phase decreases to M2L. So it has got solid and liquid phase, okay, at state 2. And liquid mass, so this is the mass of liquid phase. So this is the mass of liquid phase at, this is not total mass, let me tell you that. Okay, I'll explain it once again. So right now I'm just writing the data. In state 2, the specific internal energy of the solid phase is U2S, okay, and that of liquid phase is U2L. The sachet mass does not change during this process. Express the heat transfer of the sachet in terms of the above quantities. There is no change in the shape and size of the sachet. Okay, now we have to talk about phase change material. So you know that for changing the phase, like you are having liquid, you are supplying, so you're having water in liquid phase, okay, and you are supplying heat. After some time, what will happen? It will start to, the temperature of the water will start to increase, right? And after increasing, it will reach a point called boiling point. So for water at atmospheric pressure, it will be around 100 degrees centigrade. So the water reaches 100 degrees centigrade of temperature. Then what is happening is there won't be temperature change after some time, right? For some time there won't be temperature change, but you will see another phenomena which is called evaporation. So evaporation will happen, and all of this heat that is supplied to the water is is not used for change in temperature, that is change in internal energy. It is going for evaporation, which is phase change. Okay, so for phase change, the heat that is used for phase change is called latent heat. Latent heat, which is the latent heat, we will be taking it as m times uh, q. Okay, so this is what is, so sorry, okay, so there is something called latent heat. One second. uh, okay, q equal to latent heat, q equal to ml. L is the latent heat of whichever phenomena is happening. Here it is latent heat of vaporization. Okay, okay, vaporization. So q equal to ml. Okay, so phase change. So you can understand that when there is a phase change material is there, which is changing its phase with temperature, I mean heat being given. So the material will absorb all the heat. That means there won't be any internal change in internal energy. Okay, so this, with this thing, with this property of that material, we can use it to maintain the internal energy or the temperature as constant. So you have, suppose you have got here what they are saying is there is this chilled food items, right? So chilled food items is taken out for delivery. So out for delivery means like this will be around 0 degree centigrade, and atmospheric temperature is around 25 degrees centigrade. And so because of this change in temperature, heat flow will be happening. But if you have got a PCM material over here, this heat transfer will be taken by this PCM material. In order to change its phase, it will be using that temperature I mean heat input. Okay, so with that heat input, what it will do is it will change its phase, so that heat will be getting absorbed by the PCM material, and this internal sorry, the interior temperature will remain as at 0 degree centigrade. So this is PCM. Okay, It's a very a widely used application of PCM material is for this food processing and you know transport of food processing and all those things. Yeah. So so using mass conservation, how can we um, write this thing? So U, so this is small letter U given, that is specific internal energy that they have said. So U2 S times M2L will give you Q of solid. Okay, because there is no work done, so U equal to Q. So this is how, so this capital U is written as specific energy, specific internal energy times mass. So that is Q of solid at state 2, and then Q of liquid phase at state 2 is equal to, sorry, this should be M2S, M2L times U2L. Okay, this is at liquid phase. Now, initially, for state 1, how will we write that? Q, only liquid phase was there. That is M2L times U, sorry, not 2, it is 1. M1S, right? Sorry, there was not solid phase, so M1L times U1L, but that is not given. Okay, so what is happening is this internal energy of solid, mm, 1 second. Okay, okay. So you can see it in this manner. Q, the total heat transfer that has happened, can be written as M1L U2L, that is the U of okay. So this is the same. Why there is no different U given for the first state is because internal energy of that liquid is staying same. Okay, so U, because the temperature is maintained, right? Yeah, yeah. Okay, so this is U2L and U2L equal to U1L. Okay, because internal energy of liquid phase is not changing because the temperature is not varying. Okay, so M1L times U1L we have to write, that is U2L, that is the liquid phase um, 1 internal energy, minus M2L times U2S. Okay, that is the internal energy of the solid phase. So the M2L means that much of liquid is remaining, so that is the solid phase internal energy. Okay, this is the heat transfer that has happened. Okay, now so that's for week 2 lecture. I hope everybody understood the lecture. So thank you, and if there are any queries you can leave me a message. Thank you.